Yes, sir.
Okay, so start the chapter number 3, the electrostatic. So let's see the outline of this chapter. First, we shall understand the Coulomb's law of electrostatic, then electric field strength, electric flux density, relative permittivity, dielectric strength. So all are the terms related to the electrostatics. Then we see the capacitor in parallel and series connection. Then its related examples, capacitance calculations for parallel plate capacitor, calculation of capacitance of multi-plate capacitor. So this is the outline of this chapter number 3, electrostatics. I think all of you all learn this all this topic in your 12th standards. Okay, so just revise all these things. So let's start the first topic, Coulomb's law of electrostatics. So there are two laws of Coulomb. First law says that like charges repel each other while unlike charges attract each other. Yeah. So you can see this graphically also, plus and minus both are attracting with each other, and like charges means same charges, negative negative or positive positive, that repel from each other. So that is a Coulomb's first law. Then Coulomb's second law. So Coulomb's second law says that the magnitude of the electrostatic force between 2 point charges, it is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. Suppose two charges Q1 and Q2 place. So the force acting on these charges is directly proportional to the product of the magnitude of these two charges, this Q1 and Q2, and inversely proportional to the square of the distance. Suppose distance is d, so it is inversely proportional to the square of the distance. So you can write this equation of force acting on these charges like this way: F is equal to K, Q1 and Q2. These are the magnitude of two charges, and divide by square of the distance. So if the distance between two charges Q1 and Q2 is d, so it is d square. So that is a force acting on these charges. Here K is a constant. The value of K is 1 upon 4 pi epsilon 0 epsilon r. Here value of epsilon 0 is constant, which is 8.854 into 10 raised to minus 12. And ER, that is nothing but relative permittivity. So if you measure this force acting on the charge, and this charge is placed on air or vacuum, then the value of this relative permittivity ER is 1. So value of K is only 1 upon 4 pi epsilon 0. This one. Okay. So the equation for the acting force on these charges when it is placed in air and vacuum, then you can use this equation: 9 into 10 raised to 9 Q1 Q2 divided by d square. This 9 into 10 raised to 9 you get from this value, 1 upon 4 pi into 8.854 into 10 raised to minus 12. So you get 9 into 10 raised to 9 approximately. So for air and vacuum, you get the force equation from this value. You get the force value from this equation. And if is there any other medium, if the Q1 and Q2 charge placed in other medium, then you use this equation. Only difference is what? Here the value of relative permittivity is there. It is not 1. For different medium, the relative permittivity is different. But for air and vacuum, it is 1. Okay? So this is a force equation for air and vacuum, and this is a for any medium. So this is a Coulomb's first law and second law. I hope it is clear to you. So next term, electric field. So what is called as electric field? So the definition is that in space or in a field which a charge experience a force, that is called as an electric field, or it also called as an electrostatic field. So suppose here you can see that the one sphere of positive charge, and near to that one unit positive charge is placed. Here 1 coulomb positive charge is placed. So what happened? In this diagram, you can see that the positive charge sphere, isolated positive charge sphere, that field is directed away from this sphere because it is positively charged. So force acting on this unit positive charge, and that is near to this positive sphere. So unit positive charge placed near it that experience a force, and this force is directed radially away from this sphere. It is away from this sphere. Exactly opposite if negatively charged sphere, and near to that if positive charge is placed, so that positively charged 1 coulomb experience a force that is towards the sphere. You can see in this figure the direction of force is towards this sphere. In positive charge it is away from the sphere. So that is depend upon the polarity of the charge. The direction of force is act on any charge which is near to this positive or negative charge. So direction of electric field, that is radially outward in positively charged. In negatively charged sphere, in this figure, the force acting on unit positive charge, that will be directed radially toward the sphere. Okay. So that is about the direction of force and electric field. Then you can see this figure, two opposite charge, positive and negative charge, is placed near to each other. So the direction of the electric field between positive and negative charge, you can see that the electric field direction in positive charge, that is away from the sphere. You can see that is away from the sphere, and negative charge, the direction of the electric field, that is towards the sphere. So that is shows that the direction of electric field when two opposite charge placed near to each other. And this figure, you can see that both negatively charged sphere placed near to each other. So it is look like this way. Similarly charged bodies. Okay. Next definition, the electric field strength. The symbol is E. So the definition that the electric field strength at a point in an electric field is nothing but a force acting on a unit positive charge placed at that point. So when any unit positive charge is placed in the electric field, and if that unit positive charge experience any force, that is called as the electric field strength. As the force is more, the electric field strength is more. So it's the direction is in the direction along which force is acting. So the direction of the electric field strength is in the same direction in which force is acting. So the equation of electric field strength at a point E is equal to force divided by charge, unit positive charge. So unit of this electric field strength is Newton per coulomb. Unit of force is Newton. Unit of charge is coulomb. So electric field strength unit is Newton per coulomb. So here F is nothing but a force which is acting on this Q coulomb, and Q is nothing but a charge in coulomb placed at that particular point. I hope you understand the definition of electric field strength. Now next definition is electric flux density. So you know the definition of electric flux density? Anyone? Yes, anyone know this definition of electric flux density? Or you know the equation of?
It is defined as the electric flux passing per unit area at right angle to the direction of electric field.
Yes, very good, very good. So the definition of the electric flux density is flux per unit area measured at the right angle to the direction of the electric flux is known as the electric flux density. So in short, we can say that flux per unit area. Its symbol is D. It is denoted by D, and its unit is coulomb per square meter. So you can see the equation D is equal to psi divided by A. Psi is the symbol of electric flux. So it is flux divided by area in meter square, through which this flux is passing at right angle to the electric field. So the definition, as per the definition, equation is D is equal to flux per area, flux per unit area. Clear? Now next topic is relationship between electric flux density D and electric field strength E. So here you can see that one positive charge is placed at that point, and 1 unit positive charge, 1 coulomb, is placed at the point E. And the distance between this plus Q charge and 1 coulomb charge is D. So from this figure, we identify and derive the relationship between the D and E, electric flux density D and electric field strength E. So consider that this positive charge placed in a medium of relative permittivity ER. Suppose that Q coulomb is placed in any medium which has the relative permittivity is ER. So to determine the electric flux density at point A here, consider an imaginary sphere which passing through the point A and having the radius D. So suppose assume that this is a one large sphere and center of this sphere is A point. So radius is what? D. And this sphere is passing through this point A. So electric flux animated by this positive charge Q in all directions, that is equal to Q coulomb, and the surface area of this imaginary sphere with radius is D is equal to what? 4 pi D square. As you know the equation of area of sphere, if radius is R, then the area of sphere is what? 4 pi R square. Here radius is D, so surface area of this imaginary sphere is 4 pi into D square. So as per the equation of electric flux density, that is equal to what? Flux divided by area. So flux is what? How much? So that is equal to Q coulomb. Clear? So Q divided by area, it is 4 pi D square. So that gives a flux density at point A, at this point. Again I repeat, consider the charge of Q coulomb placed in a medium of relative permittivity. So here Q coulomb is placed in any medium which has a relative permittivity ER. And to determine the electric flux density at the point A, consider the large sphere which has a radius of D, which is nothing but the distance between this plus Q and this 1 coulomb charge. So we derive the equation, it is equal to flux per area. So flux is nothing but Q. All the electric flux from this charge body is equal to Q coulomb, and area of this sphere is 4 pi D square. So the electric flux density at A, that is equal to Q by 4 pi into D square. Now let's derive the relationship with the electric field intensity. So now derive the equation of electric field intensity at the same point A. In the same figure, we derive the electric field strength at point A. So as you know, the equation of electric field strength is what? Force per unit charge. Yeah. So what is the equation of force? Q1 Q2 divided by 4 pi epsilon 0 into epsilon R into K. Clear? And K is replaced by this 1 upon 4 pi epsilon 0 epsilon R. So if force per unit charge, electric field intensity, you get this equation. So force equation is what? Q1 and Q2. Here Q1 is what? Our Q charge, this one, and Q2 is what? That is nothing but 1 coulomb. Clear? So two charges, multiplication, Q into 1 divided by 4 pi epsilon 0 epsilon R and multiply with the D square, which is the distance between these two charges, Q coulomb and 1 coulomb, and per unit positive charge. Unit positive charge means 1 coulomb. So if you divide this F with the 1, so it is same like this equation, Q into 1 divided by 4 pi epsilon 0 epsilon R into D square. So finally you will get the equation 1 upon epsilon 0 epsilon R from this equation, and Q divided by 4 pi D square. So what is Q divided by 4 pi D square? That we have derived in the previous slide. Q divided by 4 pi D square is what? That is nothing but flux density at the point A. So replace this Q divided by 4 pi D square by D. So E is equal to what? 1 upon epsilon 0 epsilon R into D. So this gives a relationship between the electric field strength E and electric flux density D. So in other words, we can say that the flux density D at any point in electric field, that is epsilon 0 epsilon r times electric field intensity. So if you make the equation of D from this equation, so it becomes what? D is equal to E multiply epsilon 0 epsilon r. So it can say that electric flux density is E0 into ER times electric field intensity at that point. So this equation gives the relationship between flux density and electric field intensity at the same point. Then next point is absolute and relative permittivity. So as we know that different insulating materials have different relative permittivity. Only air and vacuum has the same permittivity, same relative permittivity, that is equal to 1. So if insulating material is placed between two parallel conducting plates and charge is placed on that plate, so electric field is produced in the medium between the plates. The medium is insulating material. So when any positively charged plates in between that, if we put any insulating material, so electric field is produced in this insulating material. And the intensity of this field produced in this insulating material, that is depends on the dielectric material. It means it depends upon the insulating material. We know that there are different type of insulating material, paper, mica, and all this porcelain. Okay, so depending upon the type of insulating material is placed between two conducting plates, the intensity of the field is decided based on that material. Okay, so how to find out the intensity of the field? So that is by using the permittivity. So what is the permittivity? So it is nothing but ability of the dielectric material. When I say the dielectric material, it means it is an insulating material. So ability of the dielectric material to permit the electric field to be passed through it is called as the permittivity. It means if flux is passing through any insulating material, that gives the permittivity of that insulating material. If more flux pass through the insulating material, then its permittivity is high. If low flux pass through the insulating material, then its permittivity is low. That depend upon the type of material we use. Okay? So that is denoted by epsilon. Permittivity is denoted by epsilon. And this is also called as the absolute permittivity. That is called as the absolute permittivity. So equation of E is what? Epsilon 0 into epsilon R. But for the vacuum and air, which is also dielectric material, that also have a permittivity. But in this air or vacuum, relative permittivity is 1. So equation of E is what? That is same as your epsilon 0. Equation of E is epsilon 0 epsilon R. But for vacuum and air, ER relative permittivity is 1. So permittivity is equal to what? Epsilon 0. And value of epsilon 0 is 8.854 into 10 raised to minus 12. And its unit is Faraday per meter. So I think all of you understand what is the permittivity, what is relative permittivity. Relative permittivity, that is different based on the different insulating material, but epsilon 0 is remain constant for all material. Okay? For air and vacuum, relative permittivity is always 1. Okay? Now, when permittivity of air and vacuum is taken as a reference and the permittivity of other dielectric material is compared with this air or vacuum, so we get the relative permittivity of that material. So as I already told you that E is equal to epsilon 0 into epsilon R. So epsilon R relative permittivity is equal to epsilon divided by epsilon 0. So epsilon is what? Absolute permittivity of that material. E0 is absolute permittivity of air or vacuum, and ER is nothing but a relative permittivity of the material which we have measured. Clear? So this is a relation between the permittivities. Now let's see the different terms related to the electrostatics. So first term is the electric potential. So what is electric potential? So the definition is that in electric field, electric potential at a point is nothing but a work done required to bring the unit positive charge from infinite to that point against the electric field. So it is nothing but amount of work done is required to bring the unity positive charge. It may be a negative or it may be a positive unit positive charge from infinite distance to that point against the electric field. If the direction of electric field is from right to left, then we require the force to bring the unit positive charge from right to left in opposite direction of the field. That work done, that is called as the electric potential. So the unit of electric potential is volt. The equation you can write, it is work done per unit positive charge. So equation is W divided by Q. W is the symbol of work done and Q is the symbol of charge. Clear? So this is the definition of electric potential. Amount of work done is required to bring the unity positive charge from infinite distance to that point against the electric field. Next definition is electric potential difference. So it is nothing but a difference between two electric potential. Suppose electric potential at point A is VA and electric field potential at point B is VB. So the difference between the electric potential between A and B, that is VA minus VB. Clear? So that equation we can write down like this way. Q divided by 4 pi epsilon 0 epsilon R into 1 upon D1 minus 1 upon D2. So why this electric potential is created? Because of the charge. So this D1 is nothing but a distance between this unit positive charge and point A. And this D2 is nothing but a distance between point B and unit positive charge. So the difference between two potential V and minus VB, that is difference. You can write down by this way. Third definition is potential gradient. So what is called as a potential gradient? So it is nothing but a change in the potential due to the change in the distance. Here is a mistake, printing mistake. It is not a charge, here it is a change. Okay. So read like this way: the change in the potential due to change in the distance in the direction of the electric force, that is called as a potential gradient. So change in the potential is what? V minus VB, or you can say that delta V dV. So change in the potential to the change in the distance. So distance, change in the distance is dx. So the equation is potential gradient is equal to change in the voltage dV divided by change in the distance, because the definition is change in the potential due to the change in the distance in the direction of electric force, that is called as a potential gradient. So you can write down like this way: G is equal to dV by dx. G is the unit of or symbol of potential gradient. dV is the change in the potential, dx is the change in the direction. So change in the potential per unit change in the distance, that is nothing but a potential gradient. All of you understand this, all these three definitions? Is there any doubt? Anyone? Yes or no? Anyone?
No, sir.
Okay. So next definition, dielectric strength. So what is the dielectric strength, and in which material we generally measure the dielectric strength? Can anyone give me the answer? In which type of material we generally measure the dielectric strength, and what is the meaning of dielectric strength? Can anyone give the answer? Yes? Anyone? Dielectric strength. In which type of material we generally use? So dielectric strength we generally measure. Yes?
Capacitors.
No. In the capacitance we measure
specific resistance.
No, not for resistance. Specifically, we measure for the insulating material, which is placed in the capacitance between the two parallel plate capacitors. Yeah. So for the different insulating material like mica, paper, all the different insulating material has a different dielectric strength. So what is the meaning of this dielectric strength? As per the definition, is nothing but a maximum voltage which a unit thickness of dielectric material can withstand without it being punctured. So if I'm saying in the short sentence, then suppose if you apply the voltage difference in any insulating material, suppose I take mica as an insulating material, and if you apply the potential difference across this mica in 1 unit thickness and voltage difference across this insulating material and increase this voltage till your insulating material is breakdown. So this maximum voltage at which your insulating material is breakdown, that is nothing but a dielectric strength of that material. Suppose the mica is breakdown at 10 kilovolt, so we can say that the dielectric strength of that mica is 10 kilowatt, because at 10 kilowatt your mica insulating material is breakdown. Clear? So that measures the how much amount of voltage it can withstand. So as more voltage it can withstand, then we can say that more dielectric strength of the insulating material. So the definition says that the maximum voltage which unit thickness of dielectric material that can withstand without being punctured. Without being punctured. It means just before it is punctured, how much voltage can withstand? So that is nothing but a potential, or sorry, that is called as a potential or dielectric strength of that insulating material. Or with other words, we can say that a minimum potential gradient which is necessary to break down the insulating material. Minimum potential required to break down the insulating material. So as we know that suppose 10 kilowatt mica is breakdown, so minimum potential required to break down this mica is 10 kilowatt. So that is a dielectric strength of the mica. Or in other word, you can say that maximum voltage at which dielectric material that can withstand without being punctured or without being strength. Yeah? So that is nothing but a dielectric strength of the insulating material. So what is the relationship between the dielectric strength and the thickness of insulating material? So both are inversely proportional. So the dielectric strength of the material is decreases as you increase the thickness of the insulating material. As the thickness of insulating material is large, high, then dielectric strength of that material is low. It means for the low voltage, your insulating material is punctured if the thickness is high as compared to the lower thickness of the insulating material. So both are inversely proportional to each other. Now, next topic is we go for the capacitor. So what is called as a capacitor? So all of you know that the capacitor is nothing but when any dielectric material or any insulating material is placed between two conducting plates, so that forms the capacitor. That forms a capacitor. So you can see here in this figure, these two conducting plates, in between that we put the dielectric material. Dielectric material may be anything. It may be a paper, it may be anything. Yeah? So that is called as a capacitor. So what is the function of capacitor? What is the function of capacitor? Yes, anyone?
Store the charge.
Store the electric charge. Okay. So how to measure that this capacitor store this amount of charge? By using which parameter we can calculate the capacity of the capacitor?
Q equals to CV.
Q is equal to
CV.
What is the name of that term? What is the name of the term which we generally use to measure the capacity of the capacitor?
Capacitance.
How much?
Capacitance.
Yes, capacitance. So the capacitance is nothing but a property of the capacitor to store the charge is called as a capacitor. Clear? So sometimes some students are confused about what is a capacitor and capacitor. So capacitor is what? That is a physical things. Physical things means you can see here this dielectric medium placed between two parallel plates. So that forms the capacitor. That is called capacitor. But capacitance is what? That is nothing but a property of the capacitor to store the charge in terms of electricity. That is called as a capacitor. So capacitance and capacitor both are the different things. Capacitance is the property of the capacitor, or we can say that it is the capability of the capacitor to store the charge on it. Okay? So as the charge on the plate is proportional to the potential difference applied across the it. So as we know the equation, Q is equal to charge on the plate that is directly proportional to the potential difference applied across the plate. Suppose potential difference across the plate is V, so amount of charge is directly proportional to this voltage, and its constant is C, that is nothing but a capacitance. So C is equal to what? Q by V. Q is what? Charge on the plate of this capacitor, and V is nothing but a potential difference across two plates. So that is all about the capacitance and capacitor. All of you got this? Is there any doubt in this topic, capacitor and capacitance? All of you understand the difference between these two? Okay. So
Yes,
next point, capacitance of parallel plate capacitance. So how to measure the capacitance of two parallel plate capacitors in which we have uniform dielectric medium. Suppose it is air, so we have uniform air between these two plates. If is there any other insulating material, so that is uniformly provided between these two plates. So M is positively charged plates, N is negatively charged plates. The relative permittivity of this dielectric material is ER. Distance between two plates is D. So how to measure this capacitance of this parallel plate capacitor? So consider these two plates which have area A meter square and separated by a dielectric thickness of D meter. You can see here both are separated by the D meters with relative permittivity ER of this dielectric material. And let's assume that charge Q is established on the plates by application of the V volt across these two plates. So when you apply the potential difference of V volt, and that creates the charge. So electric field between the plates is uniform because the dielectric material between these two plates is uniform. If different dielectric medium between two plates, then electric field is different. Clear? As we see that it decided based on the type of insulating material we use. So different insulating material has different permittivity. Clear? So if there is air only, then electric field is uniform throughout this distance D. If two different insulating material, suppose air and mica we use, so electric field is different, mica as well as air. So the equation of this parallel plate capacitor, electric flux density is equal to Q by V, that we already derived. Flux per unit area, or charge per unit area, that is give the electric flux density for this parallel plate capacitors. Same way, electric field intensity is nothing but what? Electric potential per unit distance. So it is V by D. As we know the relationship between electric field intensity and electric flux density, so D is equal to epsilon 0 epsilon R into E. So from this equation, if you replace this D by this equation Q by A, so it is look like this way, and replace this E by V by D, so it is epsilon 0 epsilon R V by D. So if this V comes here, replace this A, and A comes here at this side, so Q by V, that is what? Nothing but a capacitance of this capacitor. So equation of capacitance becomes epsilon 0 epsilon R A by D. So C is equal to epsilon 0 epsilon R A by D. So this is the equation you can use to find out the capacitance of any capacitor. So in this, you first calculate the area of the plates, and you must find out the distance between these two conducting plates, and you also know the absolute permittivity, relative permittivity of that insulating material. So you can find out the capacitance of that capacitor. So that equation we use during the calculation of example related to calculation of capacitor. So remember this equation, C is equal to epsilon 0 epsilon R divided by D. Now next point we see that suppose two different insulating material is placed between two conducting plates. So here in this figure you can see that one insulating material has relative permittivity ER and other is air. So as you know that air permittivity is what? Is equal to epsilon 0 because relative permittivity for air and vacuum is 1. So epsilon is equal to epsilon 0 for air. And one is the insulating material which has relative permittivity ER. And this thickness of this insulating material is T. And the total distance between two plates is D. So as you can see in this figure, medium which consists of partly the air, this one is the air which has a permittivity epsilon 0 with the parallel sided dielectric slab. This is a dielectric slab of thickness T with relative permittivity ER. So dielectric flux density D is equal to Q by A, that is remains same for both the medium. Flux density that is remains same for both the medium, if it is air or is there any other insulating material. But electric field strength, it is different. So for insulating material which has relative permittivity ER, that electric field strength E1 is equal to electric field density, electric flux density divided by epsilon 0 into epsilon R. Clear? As you know the relationship between E and D. So you can use this equation for any insulating material. But for air, in the air, electric field strength is equal to what? D by epsilon 0. Because in the air, ER is 1. Relative permittivity is 1. So what is the potential difference between these two plates? Suppose assume that is V. So it is nothing but a potential difference across this insulating material which has a thickness of T plus voltage difference across this medium air between the two plates. So you can see that V is equal to potential difference between two plates is equal to E1, that is nothing but a electric field strength of this insulating material into the thickness of this insulating material. It is T. So E1 into T plus electric field intensity in air, which is E2 into distance from this point to this point. So this distance is how much? Total distance between two plates D minus this thickness of this insulating material. So it is D minus T. So ET into D minus T, that gives the voltage between these 2 points. Clear? So total potential difference V is equal to E1 into T plus E2 into D minus T. So as you know that E1 is equal to what? D by epsilon 0 into epsilon R. So replace here. And E2 is D upon epsilon 0. So we replace here. So taking the common D by epsilon 0. So equation becomes T divided by epsilon R plus D minus T. So that gives a potential difference. Again simplify this. So D is what? The equation of D is what? Q by A. So replace D by Q by A. So it becomes Q divided by epsilon 0 into A. And the remaining term is as it is D minus T by epsilon R. Yeah. So from this equation, if you make Q by Q by V, so that becomes epsilon 0 into A divided by D minus bracket D minus T by epsilon R. The Q by V, that is nothing but capacitance of capacitor. So when any two mediums are placed between two conducting plates, so you can use the value of capacitance, this equation, to find out the capacitance of this capacitor. So it is epsilon 0 into A D minus T. Here T is nothing but a thickness of insulator, and ER is the relative permittivity of that insulating material. So here suppose only air is present in this dielectric medium between the two conducting plates. So T is 0 because there is no any other dielectric medium, only air, and relative permittivity is 1. So directly you can use this equation, epsilon 0 A by D. Here, that is the same equation here as we derive for this point. So if you derive for the air medium, at that time the value of relative permittivity ER is 1. So it is epsilon 0 epsilon A divided by D. So depend upon the different insulating material, they have different value of the capacitance. Clear? So in the example calculation, we will see it, how to calculate the capacitance of this capacitor. Same way, here you can see that there are 3 different dielectric material is placed between the 2 conducting plates. So suppose that first dielectric medium has electric field intensity E1, which has relative permittivity is ER1, or the width of this insulator. You can see that V1 is equal to E1 into D1. D1 is the thickness of this insulating material, and E1 is the electric field intensity. So E1 is what? D by epsilon 0 epsilon R1. Epsilon R1, that is the relative permittivity of this medium, and into distance or thickness of this insulating material. Same way for the second dielectric material, which has electric field intensity E2 and which has a thickness of D2, relative permittivity is ER2. So you can find out the voltage across this insulating material is V2 is nothing but E2 into D2. D2 is replaced by D by epsilon 0 epsilon R2. Epsilon R2, that is the relative permittivity of this insulating material. Same way for the third insulating material, D divided by epsilon 0 into epsilon R3 into D3. So take common D by epsilon 0. So it becomes D1 upon epsilon 0, D1 by epsilon R epsilon R2 plus D3 epsilon R3. And replace this D by Q by A. So it becomes Q by epsilon 0 into A. That term is as it is. So Q by V, this is the equation of V, total voltage across this 3 dielectric medium, across these two plates. So it is V. So Q by V, that gives 0 into A divided by this D1 upon epsilon R1 plus D2 upon epsilon R2 plus D3 upon epsilon R3. So for 3 dielectric medium, if you require the value of capacitance across these 2 plates, then you can use this equation. All these 3 medium has different insulating material. So they have different relative permittivity, ER1, ER2 and ER3. Clear all of you? Capacitance for different dielectric medium. What is the capacitance?
Yes,
Only for air. Then what is the capacitance for different dielectric material?
Yes.
Okay. So let's calculate one example so you can easily understand this. So let's see this example. Parallel plate capacitor has plate area. All of you first understand this example, thereafter you write this example. So parallel plate capacitor has plate area 4 centimeters square, and plates are separated by 3 slabs of different dielectric material or different insulating material of thickness 0.3, 0.4 and 0.3. So this is the distance or thickness of different insulating material. So D1 is 0.3, D2 is 0.4, D3 is 0.3 millimeter. Here it is given in millimeter. With relative permittivity of all this dielectric material is 3, 2.5 and 2. So ER1 is 3, ER2 is 2.5, ER3 is 2. So calculate the combined capacitance and dielectric stress of this capacitor. And here supply voltage or voltage across this capacitor is 1000 watt. So how to calculate? So as we know the equation, we apply this equation. C is equal to Q by V. Clear? So D1, D2, D3, you already know, that is given. ER1, ER2, ER3, that is already know, that is given. Area is already given, that is 4 centimeters square. Convert into meters, so it is 4 into 10 to minus 4 meters square. Area D1, D2, D3, that is given. Relative permittivity is given. So just apply this equation. C is equal to epsilon 0 into A divided by D1 upon epsilon R1 plus D2 upon epsilon R2 plus D3 upon epsilon R3. Epsilon 0 is 8.854 into 10 to minus 12, which is a constant value. You remember this value?
Sir, can we solve it and then tell you?
Okay, no problem. Solve this
Okay, sir.
and give me the answer. Answer. Yes, anyone? Get the answer?
Sir,
Yes, yes.
uh,
Yes, please.
so
What
we
is the
can take
answer?
the value of epsilon naught is equal to 8.8 into 10 raised to power minus 12.
Yes, yes, yes. So your
But we
answer
have to take,
is yes.
so we have to take up to three digits or up to 2 digits or 1 digit is fine. Means the epsilon naught after dot.
Epsilon 0 you can take up to 3 values, 3 digit, 8.854. Okay. And convert this distance into meter. So it is
Yes.
0.3 millimeter. So convert into meter. 0.3 into 10 raised to minus 3. Same way 0.4 into 10 raised to minus 3. Same way 0.3 into 10 raised to minus 3. So answer is 8.84 into 10 raised to minus 12 Faraday. So minus 12 means it is a picofaraday. So answer is 8.64 picofarad. All of you get this answer? આવે છે બધાને answer?
Yes, sir.
Yes, sir.
Yes, sir.
Sir.
Yes, sir.
Okay, very good, very good. So Next example I give you the homework. Okay. Next thing is remaining. Here we require to what? Find out the capacitance as well as dielectric stress. Okay. So how to measure the dielectric stress or dielectric field intensity? So first we know that electric field intensity, electric flux density, D is equal to Q by A. So here Q is unknown quantity. So Q we derive from this equation, C into V. Supply voltage is given 1000 volt. C we already derived, 8.64 into 10 raised to minus 12 into 1000 volt. So that give you a charge 8.64 into 10 raised to minus 9 coulomb. So put this value Q here in the equation of flux density, Q by A. Area is given 4 into 10 raised to minus 4 meter square. So you get the finally answer, electric flux density D is equal to 2.16 into 10 raised to 5 coulomb per meter square. Unit of flux density is what? Coulomb per meter square. So finally we get the answer of electric field intensity for first dielectric material, because here there are 3 different dielectric material which has a permittivity ER1, ER2 and ER3. So here I measure the first dielectric field intensity for first material. So that is nothing but D upon epsilon 0 into epsilon R1. So you get the value 813.2 kilowatt per meter. Yeah. Same way you can calculate for the second medium. So E2 is equal to D upon epsilon 0 into epsilon R2. D is remain same for all the dielectric material. Electric flux density that is remain for all, that is remain same for all the dielectric material. Just changes what? Relative permittivity, ER1, ER2 and ER3. So same way calculate E2 and E3 for other 2 dielectric materials. Yeah? That is for your homework. So write down this. First calculate Q, then flux density D, and then find out electric field intensity for first dielectric material. Same way calculate E2 and E3. That give you 4 homework. Clear all of you here? And out up to this? Yes, anyone? कोई doubt છે ભાઈ example માં or in this lecture? Is there any doubt in any one topic, any topic?
No, sir.
Okay.
No, sir.
Okay. So I think some of the students have doubt in the assignment too. Can tell me what is the doubts? Here I have a assignment 2. Here there is a one mistake here in example number 2, that VC is equal to minus 2.5 volt. Okay, but actual answer is minus 5 volt. This is a printing mistake. In example 2, assignment number 2, the voltage at node C, VC, that is equal to minus 5 volt. Okay, here. That is a printing mistake.
And sir, in question 1, are the answers correct?
Yes.
Sir? In question 1, are the answers correct which are given in the solution?
In this question number 1, assignment
Yes.
2.
Yes, sir.
Yes, answer all are right. Yes.
Okay.
I give the solution of one of the students which write the correctly all the answers. Okay. So identify your errors, whatever mistake you have done, and identify that and correct it. Okay. So I have a assignment 2 of these students, Jikil Shah. Yes, Jikil Shah. They write all answer correctly. Yes, many of the students also write this correctly answer all the questions. So for a reference, I share this PDF of these students. So identify your mistakes and correct it from them. Clear, all of you?
Sir, so one more thing. Sir, is star delta formation in the syllabus?
No. It is not in your syllabus. By mistake, it is written in your syllabus, but it is removed from your syllabus. Okay. So don't worry about it. It is not in your syllabus. Okay. So is there any doubt in assignment 1, 2 or 3? Anyone?
No, sir.
Okay. For
Sir,
your
in the-
reference, I have shared this PDF of the student. So correct your answer if it is wrong. Okay. Yes. Anyone?
So it's a practical assignment which has to be
Yes,
submitted.
yes, yes. So as you know that in the practical, I have shared the experiment 1, 2 and experiment 1, 2, 3. Okay. So in that Word file, you write down your conclusion in the experiment number 1. Whatever you observe, whatever you study in the experiment number 1, because that is a study practical. So write down your conclusion in your words. In second and third practical, which is a mesh analysis and nodal analysis, we have take the reading. Okay. So write down that reading in the practical table and write down the values in theoretical table by calculating that example theoretically. Clear? So write down both the tables, theoretical and practical, and then write down the conclusion in your words. Clear? So what we prove in the mass and nodal analysis, that whatever the theoretical value we get by the mathematical calculation, same value you get by the practical, by measuring the voltage or current, by using voltmeter and current. So write down this in your conclusion. Same for the third practical mesh analysis. Write down the tables, practical table and theoretical table values, and then write down the conclusion. And submit same PDF file to me. Clear? Same like as you attach this assignment 1 and 2, same way you attach your experiment number 1, 2, 3. Clear all of you?
Yes, sir.
જે રીતે તમે assignment attach કર્યા હતા, same way you
Yes,
attach your
sir.
experiment after writing the tables and conclusion.
Okay, sir.
Okay. So I have give you the time of, I think I have give the due date of 11. Okay. So you have 3 or 4 days to complete these tasks. You have to just write the conclusion because we already write the practical value in the experiment. મેં તમને already લખાવી દીધું છે. But you have to calculate this theoretical value also. Clear? And then after match with the theoretical value with the practical value. So you can observe
Sir.
that you get the similar answer. Yes.
Sir, what is the word limit for conclusion?
No, there is no word limit, but generally you must write the conclusion in 2 or 3 lines. Okay. Not write down the whole paragraph, 6 or 7 lines. Okay. Generally conclusions are very short in 2 or 3 lines. Maximum 3
Okay,
lines.
sir.
Clear?
Yes, sir.
But all of you please write down in your words. Clear? Don't copy from anyone. Write down in your word. Whatever you observe from the practical, write down in your words. Clear all of you?